And now, in order to invoke the Minkowski's convex body theorem, we are going to study the volume of this guy, which is an ellipsoid in the geometric sense. So the volume of the set we want to study, if you write this as an integral of the indicator function against the Lebesgue measure on Rn by a change of variable formula, so let me do this carefully. Because A is equal to OT times the spectral matrix times O, and this is equal to PT times P, where you can just take P to be the diagonal matrix consisting of the square roots of the eigenvalues of A times O, and by a change of variable formula, this is equal to the integral over the domain y with yt y less than or equal to rho. Here the change of variable formula is y equal to px. And x is equal to p inverse y. And now you pull this p inverse outside and get the determinant of p inverse times this integral. But this integral is equal to the volume of the ball centered at the origin with radius square root of rho. And this determinant of P inverse is actually the square root of the matrix A taking the reciprocal, because this is P inverse. So we get the product of those two things. And by multivariable calculus, the volume of this guy has this formula. In order to invoke Minkowski's convex body theorem, we need this volume to be greater or equal to 2 raised to the power n, which means that we want to make this guy to be greater or equal to 2 raised to the power n. And the natural question would be, what is our minimum choice for rho? From here, we solve this inequality for rho. Rho will be greater or equal to, so here we take the power 2 over n of this very complicated thing. In the numerator, you have this pi raised to the power n over 2. And you simplify this, what you get is 4 over pi times this factorial raised to the power 2 over n times the determinant of A raised to the power 1 over n. This is your minimum choice for rho. It means that if you take the rho to be this guy, then the volume will be precisely equal to 2 raised to the power n. And because this set is compact, convex, and symmetric about zero, by Minkowski's convex body theorem, this set contains a non-zero vector in Zn. So there exists x in Zn minus 0 such that xt ax is less than or equal to this minimum choice of rho, which is c sub n times the determinant of A raised to the power 1 over n, where c sub n is this part. And this completes the proof of Hermite theorem by Minkowski. As I promised earlier, in the end, I shall make a remark about this constant. By Stirling's formula, from calculus or real analysis, this factorial of n over 2 will be approximately equal to this for large n. And now you compare this with this. You take the power 2 over n, and you get this factorial raised to the power 2 over n is approximately this guy, n over 2e times pi n raised to the power 1 over n. However, this part will converge to 1 as n goes to infinity, which means this guy will be approximately n over 2e for large n. So it follows that this c sub n, when n is large, is approximately 4 over pi times n over 2e, which is 2n over pi e. When n is large. This tells you that this constant given in the Hermite theorem by Minkowski will grow approximately linearly when n is large. What is really good about this constant given by Minkowski is that it is much smaller than the Hermite constant, than the constant given by the Hermite. The constant given by Hermite is 4 over 3 raised to the power n minus 1 divided by 2. So this is Minkowski's constant, and this is Hermite's constant. And you see when n is very large, this guy will be much smaller than this, which grows exponentially. And this will become an advantage for high-dimensional problems.